Well, we've covered a lot of background material. It's time to get to the heart of the matter and figure out how to estimate a random variable. In fact, this really is the heart of what's going on with adaptive filters. The big question is how? Well, we will explore different situations. Let's start first with estimating random variable when we have no observations to guide us in our estimate. This would be a worst case scenario. We're going into the situation blind, as it were. Well, if we truly know nothing about the random variable, then I guess any guess is going to be the best we could do. So let's assume that we do know something. Perhaps we have a probability density function for that random variable. So I'm going to draw a little bit of a crazy one. Maybe something like this. So this is our PDF. What could we guess? We have no observations, so we could guess the most likely value, which would be the mode, which is the peak of the distribution of our PDF. We could also guess the mean. The mean is going to be probably somewhere in here. Maybe, yeah, I don't know. I haven't calculated it, so I might be off a little bit. We get the idea. The mean is down there. We could guess the median. The median in this case is going to be somewhere near the mean. Let's put it there. What's the best one? We have some issues here. The first is, what do we mean by best? If we had a discrete random variable, we might define best as most likely to be exactly what the value is. For example, if we were rolling 2 dice and our random variable was the sum of the pips on both dice, it would range from 2 to 12, with 7 being the most likely. So we could guess 7. And approximately 1/6 of the time, it would actually be exactly 7. And so we would be very likely to get it correct. If we're dealing with a continuous random variable, the probability of getting something perfectly exactly correct is 0, because it's a function of the area under a point, and the area under a point has measure 0. So we have to come up with some other metric. One that we're going to use all the time is we want to minimize, as a function of our estimate, the expected value of the random variable minus x hat. This is called the least mean square estimate. Looking at our PDF, we can see that this may not always be the best. For example, it's looking like if we wanted to, oops, I forgot to put the square in there. If we want to minimize the mean squared estimate, it's probably going to be somewhere in the middle, maybe near our mean, for example. And yet, the actual mean value appears almost never. In fact, it's unlikely to be anywhere near the mean value. So our LMS estimate isn't always the best estimate that you would want. But for now, it's a good one that we can start investigating and seeing how things work out. So, how do we go about minimizing this particular function? Just using our standard way of finding minima using derivatives when we have quadratics. So let's go ahead and set that up. First, we will define an error just to make the bookkeeping a little bit easier. E is defined as x minus x hat. Then we can minimize this quantity by finding the derivative of the expected value of e squared with respect to x hat and set that equal to 0. Pushing through, we get this expression. So, of course, x hat here is not the random variable, so it passes out of the expectation. And we know some of these quantities. For example, we know that expected value of x will just be our mean. Expected value of x squared is something else, but recall that we are finding the derivative with respect to x hat, and so in the derivative that goes to 0. It's not a function of x hat. So now we're just going to get minus 2 mu x, and then the derivative of x hat squared is just going to be 2x hat. And we set that equal to 0, and that tells us that x hat optimal is going to be just mu x. If we had something like a Gaussian, maybe that's obvious. With this strange bimodal distribution that I drew up above, it may or may not be obvious, but the fact is the mean is our winner. So even though in this particular case the mean is between the two modes of our distribution, and so it's unlikely to actually ever appear, by choosing the mean as our estimated value variable, our estimate of the random variable, we'll have our best possible lowest mean squared error. So what is that mean squared error? Well, let's take a look. It's actually not that hard to find out. Give it a little bit of thought while I'm writing. And I'll write in real time instead of pausing the video, so you'll have time to think through it. As I put this out, you're probably there by now. If not, that's okay. You'll get there eventually to where this type of thing is automatic. But we have the expected value of our random variable x minus the mean of x squared, and we've got a name for that quantity. That is the variance of x. So let's just put that right here. Sigma x squared. So the variance actually of a random process is a measure of its power. And this tells us that the best we can do is get rid of the mean, and from there the randomness of the random process defines everything. Can we do any better than this? How can we do better? Well, not surprisingly, to do better we must have some additional information. So what could that additional information look like? Well, let's relate this back to maybe a real problem. Suppose we want to estimate the high temperature of the weather tomorrow. If we had no other information, we would have to go back to the mean value of the weather on that particular date, perhaps. If we didn't even know the date, we would just have to go to the mean value of the high temperature period for a locale. What additional information could feed into that? Well, the high temperature today could tell us a lot about what the high temperature tomorrow is going to be. And so that's the type of additional information we're looking at. So, in the case of knowing today's temperature, we have an observation for something that is related to our random variable, tomorrow's temperature. So we're going to express this mathematically as our estimate x hat is now going to be equal to some function of an observation y evaluated at a specific observation, y equals y. And so we need to come up with this function h. Now this function h, of course, may have, there may be a lot hidden in this. It may be, for example, it needs to know something about x and the relationship of y to x. And I'm not expressing that right there with the subscripts or anything, but that should be understood. So let's explore how this would work out in a formal way. First thing we need to do is formalize the relationship between x and y, and we do that with the joint PDF. So the joint PDF can be expressed as a 2D function, and this function may look something like, who knows what. I'm drawing some contours here. Maybe those are the peaks. It looks something like this. With this joint PDF, we can express the probability of both events being in a particular area as the integral over that area, shown here with this little integration. But more importantly, let's go ahead and make sure we have some intuition about how this all works. What the joint PDF gives us is if we have some observation of y, which will be on this axis, and we want to learn something about x, which is on the x-axis, then we can choose a particular value of x, or rather of y, which we'll call y1, or I think to be consistent, y equals v1 is that little value there. And what we would get then would be a distribution of x that would look like this. So this would be f of x given y for given v is equal to v1. Alternatively, we might have a different observation right here, y is equal to v2, and for this one our distribution would look something like this, peaking right about there, coming down to right about there. So this is going to be f of x given y, u given v is equal to v2. Now the first thing to notice is we have a different mean for our green versus our purple distributions, our v1 or v2. Once we have this distribution, y tells us nothing else. So what y is actually doing is effectively, by picking kind of a slice of our joint distribution, is telling us what distribution we can expect for x. and this changes based on our observation y. Once we have this distribution, then we're back to where we started, which is our optimal x is the mean of x. But that mean, of course, changes according to which distribution we end up selecting for x, given our observation y. And there we are. Now it turns out that I've done a little bit of hand waving, suggesting that this is the right solution. And so we're going to investigate this further in the next lecture and find that indeed there's no other function of y that will be better. But we'll hold off till then so I don't destroy all the suspense.